Good day. I'm Norman Wahlberger, and today we're going to look at how letters arise in algebra in the context of identities. We've had already our share of identities when we were talking about foundations of arithmetic, the basic laws satisfied by arithmetic with, say, rational numbers. For example, we observe that m plus n equals n plus m for any natural numbers m and n. So this one single expression captures at once a whole range of possible formulas valid for particular numbers. So special cases of this are, for example, 1 plus 2 equals 2 plus 1, or 2 plus 5 equals 5 plus 2, or 13 plus 24 equals 24 plus 13, or trillions of other examples you could come up with. All of these are special cases of this one law. And we also framed some other laws: the commutative law for multiplication, distributive law, associative law for addition, associative law for multiplication. In each case, the m, k's, and n's represent arbitrary numbers of a particular kind. So an algebraic identity encodes a law which is valid for generally any values assigned to the variables. This is a rule that's valid no matter which natural numbers we substitute for m, k, and n. And it's an important usage of letters in algebra. Now, there are many very rich identities in mathematics, starting from relatively simple ones to progressively more complicated ones to very rich and sophisticated identities. Let's start off by looking at some fundamental identities that are important for almost all students of mathematics. So next to the basic laws of arithmetic that we've already talked about, I think the simple quadratic identities are the next in line. We're talking about what a plus b squared is. So that's a plus b times a plus b. And all students learn that it's a squared plus 2ab plus b squared. So this is an identity that allows us to replace this with this, or conversely, this with this whenever we find it in an expression. A simple variant is a minus b squared is almost the same. It's a squared minus 2ab plus b squared. And of course, we can verify these identities by simply using the distributive law to expand a minus b times a minus b, for example. Another important quadratic identity is the difference of squares, that a plus b times a minus b equals a squared minus b squared. Next in line, I suppose, in terms of simplicity and importance, are the geometric series identities. The first one is really just a special case of this one, the fact that 1 plus r times 1 minus r equals 1 minus r squared. Now you might ask, why am I switching from a's and b's to r? Well, that's because in traditional mathematics, certain kinds of identities have certain variables associated to them. And so I'm trying to use the notation that's most commonly associated with the identities that we're talking about. A variant on this, slightly more complicated, is 1 plus r squared times 1 minus r. And it's important to verify that when you multiply this all out and collect terms, you're going to get 1 minus r cubed. Because here you have 1 plus r squared, and here you have minus r squared minus r cubed. So the r and the r squared terms cancel. You're just left with 1 minus r cubed. That kind of telescoping or collapsing of intermediate terms happens for larger expressions. If we take 1 plus r squared plus r cubed and multiply by 1 minus r, again, the only thing that's left after you expand and cancel is 1 minus r to the fourth. And then there's an obvious pattern that's established here. And we can write the general law involving not just a general letter r representing a number, but also in terms of a general exponent n, generalizing the 2, 3, 4, and so on that appeared here. So in this context, the n represents a natural number, 1 in this sequence, while the r is potentially a rational number. And this very important formula is a geometric series formula. 1 plus r squared all the way up to r to the n is 1 minus r to the n plus 1 divided by 1 minus r. It's what we get when we take an expression like this and divide by the 1 minus r. That would be the case when n is 3. And because we're dividing by 1 minus r, it's important to remember that the formula is only valid if this denominator is not 0. So we have to require that r is not equal to 1. And the geometric series formula is often written like this, slightly more general, where the first term is a instead of 1, but each term after that is obtained by multiplying by r. So the sum, a plus ar, all the way up to a r to the n, is a times 1 minus r to the n plus 1 divided by 1 minus r. Here are two special identities that play a particularly important role in geometry. The first one we could call the Pythagorean identity. And here's the simple form, that 1 minus h squared all squared plus 2h all squared equals 1 plus h squared squared. And I've decided to use h instead of some other variable for pretty good reason. Generalization of this is m squared minus n squared all squared plus 2mn all squared equals m squared plus n squared all squared. And all students of mathematics should verify this formula by explicitly expanding both sides and showing that they're in fact the same. The connection of this formula with Pythagorean triples is well known. For any values of m and n, natural numbers, we're getting three numbers here which have the property that this squared plus this squared equals this squared, giving us the sides of a right triangle according to Pythagoras' theorem. So for example, if m is 2 and n is 1, then these three numbers inside the brackets become 3, 4, and 5. 3 squared plus 4 squared equals 5 squared. And you can generate other Pythagorean triples simply by changing the values of m and n. And here are two other important identities. They're almost the same. Fibonacci's identities. This quantity squared plus this quantity squared equals this times this. And a slight variant, and I've put this one on over here. This thing squared plus this thing squared equals again the same product of things. These two identities are crucial for trigonometry and for complex numbers. So they're also important identities that all students of maths should verify by expansion. Next time we're going to talk about probably the most common and useful of all identities, the binomial theorem, which is a centerpiece of high school mathematics. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.